Okay, so starting with chapter 6, chemical bonding. Okay, now from physical science and based on what you guys told me in your What Do You Know, you're familiar with ionic and covalent bonding. Okay. I am ashamed to admit how far into my life I was still a little bit confused about these things. Through a degree in biology with a minor in chemistry, still couldn't keep them straight for some reason, because the mnemonic that no one ever presented to me. So, okay, this is so simple that you think a third grader would have it, right? Ionic bonds are formed by the attraction of ions. Ions, okay? We know what an ion is, right? It's a charged atom. It's an atom that has given up or gained electrons. We talked a little bit about making ions in the last chapter. Well, in an ionic bond, all you've got is a couple of ions that are really strongly attracted to one another, which means they want to stand shoulder to shoulder because the forces of attraction between them are so strong. We will talk a lot about forces of attraction and repulsion in this chapter and the chapters to follow. And so in an ionic bond, there is some other atom that is intrinsically attractive to another atom. We get large numbers of these things and they stand shoulder to shoulder, and it's very, very powerful. It's a very powerful kind of bond. Now, that's an ionic bond. In a covalent bond, let's break this word down. Let's do a little bit of vocabulary stuff. VALE. You see that little chunk anywhere else in the last chapter? Valence electrons. Anybody here ever participate in a sport? Okay. Anybody ever were any of you on a team where you had a team captain? Okay. Did you ever have two team captains that shared their responsibilities? What are they called? Co-captains. Covalent bonding is when two atoms are co-captains of the valence electron team, to use a really stupid, magnificently dumb kind of mnemonic, but it's true. They're sharing. Just like co-captains share responsibility, covalent bonds mean that two atoms are sharing their electrons. So the difference between ionic bonding, where we're very strongly attracted, these two, we're so strongly attracted we're going to stand shoulder to shoulder. But we're not actually sharing anything. We're just standing shoulder to shoulder. In a covalent bond, whoops, darn it. In a covalent bond, these two things are actually going to overlap and share. Remember, we have that electron cloud. What's the electron cloud? Oh, Moser, that was chapter 4. I don't know. It's all that big fuzzy ball of orbitals. Remember, we've got the tennis ball nucleus shoved into a giant wad of cotton candy, and the orbital is all that cotton candy. So in ionic bonding, the cotton candy clouds are not touching, or they're just touching. They're not overlapping. There's no interweaving of the cotton candy. For covalent bonding, we actually have those strands of cotton candy weaving together. There are electrons that are actually going back and forth between the two atoms. They are sharing electrons, fully, honestly sharing them. Those electrons are shared between them. They no longer belong to just one atom. They are shared. They are able to move between the electron clouds of the two atoms. And that's the most basic level of explanation of chemical bonding. This is what you should have gotten in physical science. Would you believe it gets a little bit more complicated? Of course you would, because every time I say, and that's what you should have for physical science, it means we're going to make it more complicated. That nice simple picture you've had, we're going to proceed to complicate things. Okay, that's the basics. I guess you could say that this is the bad news. We told you in physical science that, you know, things bond ionically or things bond covalently. It's not that simple. Actually, there's a continuum of bonding. So you know what a continuum is, right? It's like a color spectrum. We go from red, orange, green, yellow, blue, indigo, violet. That's a spectrum. Well, there's a spectrum for chemical bonding as well. And on one end, we have totally ionic. Absolutely. There is no sharing occurring whatsoever. On the other end, we have totally covalent. I can't fit all the word in there. They are sharing perfectly, 100% even sharing. Everything in the middle is a little bit of both. So this is where we get down into that idea of not sharing evenly. Not sharing evenly. Do you remember the term that we used in the last chapter to talk about even sharing of electrons? There was a very specific term we used, and we can apply it to any atom. We can talk about how evenly it shares. And the metaphor we used there was being tossed into bed, either sharing a bed with siblings or cousins, you know, over the summer, going to grandma's. You and 4 other cousins in a queen-size bed with 1 blanket. Does everybody share evenly? Heck no. Somebody always ends up with all the blankets wrapped around them, and somebody else ends up cold. Okay, what's that term for how evenly an atom shares its electrons when it's bonded? Starts with an E. Yeah? You're getting close. Electronegativity. Electronegativity. So, oh, hey, look, it was on the slide. Electronegativity. Yeah, that's how evenly an atom will share. So, based on how much of a blanket hog, how much of an electron cloud hog a particular atom is, that's what controls where on this spectrum a particular bond falls. Okay, well that's fine in theory. So let's think about that sort of conceptually before we start attaching numbers. If I have A and I have B, and they are actually sharing their electron cloud. So that's their electron cloud. Here was A all by itself, here was B all by itself. When they bond, this is obviously not to scale, they intermingle their electron cloud. Electrons are flowing back and forth. They're in this merged cloud area made up of the upper energy levels. So, if A really, 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 really likes electrons, what is that picture going to look like? So let's say that A, they are going to share. This is not an ionic bond. But A likes electrons a lot more. It has high electronegativity, and B has it's got lower electronegativity. Where is most of the blanket, where is most of the electron cloud going to fall? Around A. So we're going to end up with something that looks a little bit more like that. A will get more of the cloud. A gets more of the blankets. This is your cousin Joey who wraps up in the blankets, executes the rollover maneuver like an alligator with its prey, thereby stealing all the blankets from you and leaving you shivering in your t-shirt and shorts. You know, you don't want to have to share the bed with cousin Joey. You don't want to have to share electrons with substance A, whatever it is. Okay, so I will stop for a moment before we start getting the numbers attached here. And just describe your learning goals for the week. Now, these are from last week, but we didn't get as far last week as I thought we would. So this is where we are this week. But by the end of this week, really by the end of this unit, you're going to be able to describe the differences between ionic and covalent bonding. You can probably do that pretty well now. How well you do that in 24 hours is the real test, because we just talked about it. In 24 hours, can you still do it? Then you got it. Different types of covalent bonds, we're about to talk about that, and explain why two things bond in a certain way. Now, you have a piece of that right now, right? It's all about how much they love electrons. It's about how big of a blanket hog, how much of an orbital hog they are. The next thing, and you will be able to do this by the end of this week, you're going to be able to look at two substances and predict what kind of bond they're going to form based on their electronegativities. It's pretty easy. It's nice and cut and dry. We like things that are nice and cut and dry. There's no wishy-washiness about it. It's this or it's this. But those are the things that we're going to do this week. Okay, so the maximum difference in electronegativity between any two things ever, anywhere in the universe is 3.3. If we take the most electronegative thing that exists, which is what? Does anybody remember? Fluorine. Yeah, fluorine has an electronegativity. It's assigned an En of 4. If we put fluorine with the least electronegative thing that exists, the difference between them is 3.3. And that's the absolute max. On page 151 in your whole modern chemistry textbook, there's a periodic table of electronegativities. Will you look at that? And you can see the electronegativities for any given atom. Gesundheit. And they go all the way from, I think our lowest is 0.7, francium and cesium, and fluorine is our highest at 4. So max difference is 3.3. If you've got something with a difference of 3.3, that is a purely ionic bond. It's purely ionic. One of the substances is going to completely pull the covers off the other one. It's going to completely take the electron. It's not going to share. There's too much of a difference. There will be no sharing. You don't get a scrap of cover. Nothing. It's ionic all the way. Now, if you have two things that have identical electronegativities, hydrogen does this. So we get two hydrogens that bond. I don't have any identical twins this year. I haven't had any identical twins in a long time. I've had lots of fraternal twins. But if we have two hydrogens, and I'm drawing this terribly, they're identical. They have identical electronegativities. Those covers, that electron cloud, will be shared 100% evenly. They have the same amount of love for the blankets, for the electron cloud. So anytime we've got identical atoms, so this is all your diatomic molecules, diatomic, 2 atoms, chlorine, fluorine, nitrogen, oxygen, all those things that form a little double, a little set of identical twins. That's purely covalent. There is no unevenness to that sharing. So are you sensing that we're about to get into the gray area? Yes, that's good. Okay, if we have a difference of electronegativity of 1.7 or less, it's a covalent bond, but there are different types of covalent bonds. So there are covalent bonds where it's not really shared evenly. One person ends up with most of the blanket, one person ends up with that little corner scrap, So you can cover your knees or your butt, but you can't cover both because you don't have enough blanket. So that's called a polar covalent bond. The other kind where we're sharing more or less evenly, one person has more blanket, but the other person's still warm, is a nonpolar covalent bond. So let's examine those real quickly. If you look at that periodic table of electronegativities, let's look at hydrogen and oxygen. What's the electronegativity of hydrogen? 2.1. What's the electronegativity of oxygen? So, 3.5 minus 2.1. What kind of bond is this? It's a polar covalent bond. It's a polar covalent bond. Water is well known, so you will know Mickey by the time we're done with this chapter very well. Water forms this little Mickey Mouse. Okay? Oxygen is Mickey's face, hydrogen are Mickey's ears. And this is not drawn well to scale. I'll fix it. So we've got our Mickey here, but which of the things in that substance likes electrons more? What's got the higher electronegativity? Oxygen. Oxygen's pretty darn electronegative. 4 is your max. Oxygen's a 3.5. So in fact, what we end up with, whoopsie. In fact, what we end up with is something that looks more like that, where oxygen has drawn most of the electron cloud down. So basically, Mickey's got a really fat chin. Mickey's got like a triple chin and little tiny skinny ears if we look at the electron cloud, because oxygen is much more electronegative than hydrogen. It's able to pull a lot more of the electron cloud down around itself. So the hydrogens end up with very little in the way of electron cloud around them. Now, it's all well and good to throw out numbers and words. It makes much more sense to most people, and certainly to me, if we have a picture to go with it. I find this to be very, very helpful, actually. So if we have an electronegativity difference of 0, that is a purely covalent nonpolar bond. Okay, so between 0.3 and 1.7, we would call this a polar covalent bond. (1.7) and up, it's ionic. Any difference above 1.7, if you are the less electronegative thing, you don't stand a chance of keeping any blankets. You are the cousin in the queen-size bed who likes the blankets less. You're going to be, at some point in the night, you will just be uncovered. So if we're looking at a difference of 1.7 all the way up to the max of 3.3, that's an ionic bond. So there are now we're talking about 3 kinds of bonds here. Nonpolar covalent, what we would call pretty much purely covalent, pure sharing. Polar covalent, where they're sharing, but they're not sharing evenly. And an ionic bond, where there's no sharing whatsoever. I'm taking your blankets. Cousin Joey is wrapping up and rolling over and giggling his silly little head off. You're just going to be out in the cold. 3 kinds of bonds. So let's do some practice with these, okay? And we'll keep flipping back to this graphic. Okay, so we've got 2 examples of things that form compounds. We've got sodium and chloride. We've got iron and oxygen. Okay, so where do we get started with figuring out what kind of bonds these things are going to form? Remember, we have 3 options. Pardon? Find the electronegativities and subtract them. So sodium's electronegativity is 0.9. Chlorine's is 3. What's our difference in electronegativity? 3 minus 0.9, yeah, 2.1. Difference. It's very important to note that that is the En difference. On a test, don't you dare tell me, oh, it's got an En of 2.1. No, it doesn't. The compound doesn't have any En whatsoever. The 2 substances involved in bonding have electronegativities, and between them there is a difference of electronegativities. 2.1 is nobody's En. It's the difference. Okay, so we've got an En difference of 2.1. Where does that put us? Ionic. So this is going to form an ionic bond. Hey, you just finished your first one. You just predicted your first bond formation. And yeah, sodium chloride is a well-known ionic bond. Okay, iron and oxygen. Iron has an En of? Yes, sir.
I think I'm missing something, but
Okay.
I don't know. But where are you getting these numbers, like that 3.8?
The 3 and the 0.9 and stuff? Page 151, periodic table of electronegativities. Okay, so iron has an En of 1.8. Oxygen? 3.5. What's our difference? Okay, so we've got 1.7. Where does that put us? Ooh. Very polar covalent, yeah. Okay. Okay, we've got nitrogen and oxygen. We've got sulfur and chloride. So nitrogen, En. Yep, 3.0. Oxygen, we've already done a million times, 3.5. The En difference is, which puts us where? Yeah, this is going to be polar covalent. Okay, sulfur and chloride on your own. Let's go ahead and we'll finish this one. So this was 2.5 and 3, so 0.5 difference, so also polar covalent. Okay, it is a little tougher actually to come up with. Here, pull two things that are going to bond in this particular way. But in general, so let's look at one more example. What if bromine bonded to bromine? What's the electronegativity difference? En difference of 0. What kind of bond is that? 100% covalent. Absolutely 100% covalent. There is no unevenness to the sharing. Okay, so now we're talking about two different kinds of covalent substance, covalent bonds, polar, nonpolar. What does that mean? If there's no difference between how those things behave, we don't care that they're bonded differently, right? I mean, it's, okay, great, we can stick a name on it. A, B, C, D, E, purple, whatever. If it doesn't make a difference, we don't care. But as it turns out, things that are bonded in a polar covalent bond versus a nonpolar bond behave differently. Oh, okay. And you're actually going to do a lab probably middle of next week. Maybe this week. Maybe we can get that in. Today's Tuesday. Maybe we can do that Thursday. We'll see. They behave differently. So let's draw our Mickey again. And we're going to draw our Mickey with his skinny ears and fat chin. So there's a Mickey, and here is our bromine. Okay, so one of these is a non-polar covalent. That would be this one. One of these is a polar covalent. So in the non-polar covalent, at any given point in this molecule, you've got an equal amount of access to positive charge and negative charge, right? Which means overall this whole thing is neutral. The entire thing is neutral overall. There is no one spot on this molecule that feels more positive. There's no one spot that feels more negative. Because the electron cloud is evenly distributed over those two little tennis balls of positivity. Remember, two positive tennis balls in a giant fluffy cloud of negative cotton candy. Someday I'm going to get cotton candy in here, a boatload of it, and we are going to make the most god-awful mess when we talk about electron clouds. It will be horrible. It will be sticky and disgusting, and we will have to use the emergency shower just to ever use the room again. Maybe I should do that before we move into the nice new building, huh? Okay. Maybe we'll do that this year. Yeah, we'll have a giant cotton candy electron cloud kind of demo day. It's going to be awful. Back to our bromine. So, in the bromine, there is no one spot here that's got a positive feel or a negative feel. Every place is evenly neutral. Well, when we go to our fat chin Mickey with a triple chin, most of the electron cloud is where? Around the oxygen. Well, the electron cloud would be what? Negative or positive? Negative. Guess what? That end of the water molecule has got a little bit of a charge. It's got a partial charge. Well, what are hydrogen atoms if you strip some of their electron away from them? Yeah, they're just a naked proton. Remember the toddler Halloween costume for chemistry geeks? You just paint a plus sign on your toddler's belly and that's their whole costume. They're a naked proton. Not that I would ever do that to my child. But if you've got these two hydrogens sitting up there, guess what? That area of the molecule has got a little bit of a charge. What kind of charge would it be? Positive. So we now have Mickey. I always say Mickey's got a really negative chin. Sad little chin. Maybe he's sad because he has a triple chin. But he's got really positive little ears. So this is a polar molecule. Polar. Where have you heard that term? What has poles? The Earth, the North Pole, the South Pole. A magnet has poles. What are poles? They're areas that are opposites, right? If you think that cotton candy is food, then you and I are polar opposites on the controversial question of whether or not cotton candy is food. If you think raisins are food, you and I are polar opposites on the controversial question of whether or not raisins are food. Ugh. But, you know, those poles indicate opposites. So in a polar molecule, you've got areas of positive and negative charge. That changes the way that they behave. Because now we have one more attractive force to throw into the mix. And remember, if you've got some positives and you've got some negatives, what are you going to have? Attraction. You throw positives and negatives in together, you get attractive forces. If you have a molecule that has areas of charge on it, they will be attracted to other molecules based on their charge. So if we line up a bunch of Mickeys, for instance, in a glass, in a lake, in an ocean, in a cloud, they tend to line up head to chin because all the little negative chins are attracted to all the little positive heads. I know, it looks like a scene out of a horror film for water. I get that it's terrible. But hopefully you get the concept that when you put a bunch of polar things together, they're going to line up in a very particular way at a molecular level, which changes how they behave at a macro level. In the 2 minutes or so that we've got before the bell rings and we have 4 minutes to walk around, if you have nonpolar molecules, if you've got a bunch of nonpolar molecules in a container, are they going to line up in any particular way? No. Totally random. There's nothing that orders them. There's nothing that pushes them into a particular formation because there's no area of charge. They are really 100% neutral overall. Now, here's an important point. Is water a neutral molecule? Yes, it is. And I want to make sure this is clear because I realize how fuzzy this could be. Water is a neutral molecule. It's got an area of, it's called partial charge. So from one end to the other, one end is more positive than the other. It doesn't mean that the molecule overall is charged. So overall, water is still a neutral molecule. We're going to talk about clusters of covalently bound atoms that are not neutral later in this chapter. But water is a neutral molecule. It just happens to have a distribution of its charges. So it's got an area of, we call it partial charge and partial charge. Partial negative charge, partial positive charge. It's still considered a neutral molecule.